Welcome to the 15th lecture. In this lecture, we will study the formula to compute variance. This is the numerical formula or the computing formula that is easier to work with. If you are working by hand, you can use this formula and you can compute variance easily compared to the formula we studied in last lecture. Right. Let's start with the definition that we studied in the 14th lecture. The definition for sample variance, this is sample variance, the formula for sample variance is the summation of the difference of each data element minus the mean and then squared. And we have to add all these elements and then divide by n minus 1, where n is the number of measurements in the given data. Right, so we have to divide by n minus 1 because it gives a better measure or it gives a better estimation of the population parameter, the population variance, the variance of the population. Right, so s squared, we can apply the basic formula of a minus b squared that we studied in school. A minus b squared is a squared minus 2ab plus b squared. So this is a, this is your b, xi minus the average of x or the mean of x. So we should consider this as a and this as b. So a minus b squared is a squared minus 2ab plus b squared. So applying the same school's formula, we come up with xi squared minus 2 times xi times x bar plus x bar squared divided by n minus 1. So we have applied the school's formula on the basic expression to compute variance. We are in search of a formula that is computationally more feasible than this formula. Right, let's see and let's solve it further. S squared can further be written as this summation can be applied on each and every elements because they are assumed to be independent of each other. So summation xi squared. We know this summation. Yes, we know. We studied in last lecture or in one of our previous lectures that summation from 1 to n of xi, this means x1 plus x2 plus x3 plus xn. So it's a recap from one of our previous lectures. This is what summation means. I explained that summation is a Greek word that represents sum, addition of these numbers. So the summation operator is then distributed on these three terms, xi squared minus 2xi x bar plus x bar squared. So minus 2. Since this x bar is a constant, it's not a function of I, we can write it outside, and 2 is also a constant, and we apply this formula here, xi, and then plus this x bar squared is not the function of I, it's not dependent on I, it's a constant, therefore we'll write it outside. X bar squared summation I from 1 to n divided by n minus 1. Right, let's see what this means. Summation of I from 1 to n, and there is nothing on the right side of it. What does this mean? This means that if we have summation of numbers 1 to n, this means 1 plus 2, 1 plus 1 plus 1 plus 1 n. So this means if we have summation, this means we have to add 1 because there is a 1 here. If there is nothing here, this means a 1. So we have to 1 into a 1 n times. So if we add 1 plus 1 plus 1 n times, this is n. If we add 1 plus 1 plus 1, this is 3. If we add 1 plus 1 plus 1 plus 1 4 times. This is 4. So if we add 1 into 1 n times, this means this is n. So we can replace this as, this summation can be replaced as n, small n. Right. Whereas in the next step, we are going to put the value of x bar. In one of our previous lectures, we studied that x bar is summation from 1 to n xi's over n. We studied that this is actually the formula to compute mean over a data set, over a sample, right? So now let's plug this expression here and here, so that we come up with a better expression or a better formula to compute variance. To compute the variance, right, let's put it. This becomes summation to 1 xi squared minus 2. So instead of x bar, we write summation 1 to n xi times this over n times this 1 to n xi plus n times this x bar squared, summation 1 to n xi over n squared. So this is all the numerator, and the denominator is n minus 1. Right. So what is this? Summation xi, summation xi. They both are the same and they are being multiplied together. So we can have a square here and we can get rid of this term and replace this with a square. This is 2 over n. It's the same thing. You write either by n here or by n here. Right. And then this is n squared. You can take this n squared out of this denominator. So now the things are pretty manageable because n over n squared gives us 1 over n. Right. Now we have minus 2 over n this squared plus 1 over n this squared. This should leave us minus. This should leave minus 1 over n this squared, and this should be removed. Over n minus 1. So now we are left with a very handy formula to compute the variance. This one. This formula. What does this formula involve? This formula involves xi squared and then sum, and summing xi's and then computing a square. These are two different things. What does the first term mean? Summation over xi squared. Let's see, what does this first term mean? Summation 1 to n xi squared. What does this mean? This means x1 squared plus x2 squared plus x3 squared plus xn squared. Or in other words, this is summation over squares. In words, we write it summation over squares. We compute square of each number first and then the sum of those squares. Right. Let's see what this second term means. What does the second term means? This means summation 1 to n xi squared. This means we have to first expand this summation operator x1 plus x2 plus x3 plus xn, and once we compute the sum, we square it. So it's a bit different. It's obviously the different operation compared to this. So in words, it can be represented as a square over sum of squares. This is square of sum. So this is sum of squares. We compute squares first and then sum, and this is square of sum. We compute sum first and then square. So there is a difference of operation there's a difference of order in which the two operations are carried out. So the formula that we have just derived is called, what does this formula called? It's called the computing formula for the sample variance. This is the computing formula for sample variance. So it's computationally better, or it's efficient if you're computing something using calculator or by hand. It's efficient compared to the previous method. Oh, and we reach the same answer. This is very important. We reach the same answer in both cases, either through a difficult path or we adopt the easier path. We reach to the same answer. That's the good news. So why not adopt the easier path? So that is what this computing formula mean. We go through the easier path and we reach to the same result. Let's verify it. Here I'm going to solve an example. And the example is the same that we worked with when we were working with the basic formula that involves computing mean first. So we have xi and xi squared. Xi's are 5, 7, 1, 2, 4. This is the same data set we worked with in our last lecture. And in our last lecture, we computed mean first, and then we subtracted each data element from the mean, right? And then we computed square of each term, and then we added all those terms and then divided by n-1. So let's adopt a simpler way now. Just write all the numbers given in your data set, your first point or your first step. The second step is very easy. Compute squares. 25, 49, 1, 4, 16. That's all. And then you have to put everything in the formula. But before you go there, you have to add them. This gives you summation from 1 to 5. Why 5? Why not n? Why not n? Why 5? Because we have 5 numbers here. N is 5. Right. Therefore, we have replaced n with 5. X size. This is 5 plus 7, 8, 8 plus 2, 10, 10 plus 4, 14 plus 5, 19. So summation x size is 19 for this case. And adding this gives us summation over xi squared, because every element is squared. From I goes from 1 to 5. So this gives us 95. You can verify it at home. The answer is 95. Now it's the time to put everything in the formula. The formula is ready for you. S squared is summation. Let's modify this formula for this data set. For that, we have to replace n with 5. N with 5. and of course n minus 1 with 4, 5 minus 1. So I ranging from 1 to 5 xi squared. This summation is 95. We have squared each number and then we have summed them. We have computed the sum over this column, and the answer is 95 minus 1 over 5 times the summation over xi. The summation over xi is 19, and this squared. You have to remember this square is squared over 5 minus 1 is 4. Solving this gives us s squared 5.7. It is the same number that we reached to when we used the conventional formula or the basic formula in our last lecture. So we reached there with less effort. With lesser effort, we reach to the same answer. So that is why this formula is handy, this formula is useful, it's more efficient. Right, let's compute standard deviation, SD. Standard deviation, SD, you know it is squared, and this is also called S, small s. For sample, this is small s. For population, it is small sigma. S is 5.7. Positive square root of 5.7 comes out to be 2.39. So with this formula, we reach to the same answer. And this is the standard deviation we reach to when we use the conventional formula to compute the variance. That's all for this lecture. I have already posted the notes for this lecture. Right. Thank you.